Welcome to this video. Today, we'll explore the coding problem from LeetCode titled Longest Well-Performing Interval. In this problem, we'll work with an array of hours to find the longest subarray where workers have well-performing days. Let's dive into the problem statement and understand the solution approaches. In this problem, we're tasked with analyzing the work hours of an employee over a series of days, represented as an integer array called hours. Each element in the array corresponds to the number of hours worked on a particular day. Now, an interval in this array, defined by indices I, j, is considered a well-performing interval if the number of days within this range where the employee worked more than 8 hours is strictly greater than the number of days they worked 8 hours or fewer. The goal is to determine the length of the longest such well-performing interval. For the input, we have an array hours of size n, where each value signifies the hours worked on a particular day. As output, we need to return a single integer, which is the length of the longest interval meeting this condition. Let's consider an example to better understand the problem. Suppose the input array is hours equals 9, 9, 6, 0, 6, 6, 9. The output for this example is 3. Why? Let's examine the subarray 9, 9, 6, which spans indices 0 to 2. Within this subarray, there are 2 days where the employee worked more than 8 hours, specifically hours 0 equals 9 and hours 1 equals 9. There's 1 day where they worked 8 hours or less, which is hours 2 equals 6. Since the number of days with more than 8 hours worked is strictly greater than the days with 8 or fewer hours, this subarray qualifies as a well-performing interval. The length of this interval is 3, and there are no longer intervals that satisfy the condition. Thus, the output is 3. Now, let's look at another example to highlight a different scenario. If the input is hours equals 6, 6, 6, the output is 0. This is because there isn't any interval where the number of days with more than 8 hours worked is strictly greater than the days with 8 or fewer hours. In this case, all the days in the array have hours worked that are 8 or less, so no intervals qualify as well-performing. Hence, the result is 0. Finally, let's review one more example. If hours equals 10, 8, 9, 8, 10, 9, the output is 5. Here, consider the subarray 10, 8, 9, 8, 10, which spans indices 0 to 4. In this interval, there are 3 days where the employee worked more than 8 hours, specifically hours 0 equals 10, hours 2 equals 9, and hours 4 equals 10. On the other hand, there are 2 days with 8 or fewer hours worked, hours 1 equals 8 and hours 3 equals 8. Since the number of days with more than 8 hours worked is greater than those with 8 or fewer hours, this is a well-performing interval with a length of 5. Moreover, this is the longest interval that satisfies the condition, so the output is 5. The constraints of the problem ensure that the input size can go up to 10,000, meaning we need an efficient approach to handle large arrays. Additionally, edge cases include scenarios where all values are greater than 8, in which case the entire array is a well-performing interval, or where all values are 8 or less, resulting in an output of 0. To solve the problem of finding the longest well-performing interval, we begin by considering 2 initial approaches. The first is the brute force approach, where we generate all possible subarrays of the input array hours and evaluate each one to check if it qualifies as a well-performing interval. For a subarray to be well-performing, the count of tiring days, where hours, k, 8, must exceed that of non-tiring days, where hours, k, equals 8. While this method is straightforward to understand, it is computationally expensive. Generating all subarrays involves n squared operations, and for each subarray, counting the tiring and non-tiring days adds another n operation, resulting in an overall complexity of n cubed. This is infeasible for large inputs. The second approach is to use a prefix sum with nested loops. Here, instead of recalculating counts for every subarray, we transform the hours array into +1 for tiring days and -1 for non-tiring days. A prefix sum array is then used to store cumulative sums, allowing us to calculate the sum of any subarray in constant time. However, iterating over all subarray pairs still requires n squared operations, making it more efficient than brute force but still too slow for larger datasets. To optimize performance further, we use a hash map-based approach that builds on the prefix sum idea. First, we transform the hours array into +1 for tiring days and -1 for non-tiring days, and maintain a running prefix sum as we iterate through the array. The key insight here is that a well-performing interval corresponds to a positive sum, and we can identify this efficiently using a hash map. Specifically, for each prefix sum at index j, we look for an earlier prefix sum _sum 1. If such a value exists, the interval between those indices is well-performing. The hash map stores the first occurrence of each prefix sum, allowing us to avoid revisiting earlier elements and perform these checks in constant time. This method reduces the overall time complexity to O(n), as we only traverse the array once and use hash map operations, which are also O(1). Additionally, the space complexity is O(n), as we store only one value per unique prefix sum. This makes the hash map approach highly efficient and suitable for large inputs. The chosen strategy for this problem is the optimized hash map approach. The intuition behind this method is that a well-performing interval can be identified by tracking subarrays with more +1s, representing tiring days, than -1s, representing non-tiring days. Using prefix sums and a hash map, we can efficiently determine whether such intervals exist. The breakthrough insight is recognizing that the first occurrence of a specific prefix sum can be used to compute the length of valid intervals without recomputing sums. Comparing the three approaches, the brute force solution is prohibitively slow due to its cubic time complexity. The prefix sum with nested loops improves efficiency but remains quadratic, which is still insufficient for large datasets. The hash map solution, however, achieves linear time complexity, making it the optimal choice. It strikes the best balance between speed and memory usage, leveraging early stopping and efficient lookups to maximize performance. The implementation of this strategy involves 4 straightforward steps. First, transform the hours array into a new format, where each element is +1 if the work hours exceed 8, and -1 otherwise. Next, maintain a running prefix _sum while iterating through the array, using a hash map to store the first occurrence of each prefix sum. For every new prefix _sum, check the hash map to see if prefix _sum 1 exists. If it does, calculate the length of the interval that this represents and update the maximum interval length accordingly. Finally, once the iteration is complete, return the maximum interval length as the result. This step-by-step process is efficient, intuitive, and ensures that the solution runs in O(n) time, making it well-suited for large input sizes. To solve the problem of finding the longest well-performing interval, we begin by transforming the input array. The goal of this transformation is to simplify comparisons by mapping each day in the hours array based on whether the hours worked were more than 8 or not. If an employee worked over 8 hours, we treat it as a tiring day and assign it a value of +1. Otherwise, for 8 hours or fewer, it's considered a non-tiring day and gets mapped to -1. By doing this, our task reduces to identifying subarrays where the sum is positive, as this would indicate more tiring days than non-tiring ones. The Python code snippet provided shows how to achieve this transformation efficiently using a list comprehension. Now, with this transformed array, the problem becomes a matter of finding subarrays with a positive total. To facilitate this, we compute the prefix sum array in the next step. The prefix sum allows us to calculate the sum of any subarray in constant time, which is crucial for optimizing the algorithm. We initialize a variable prefix _sum to 0 and use a dictionary, prefix _map, to store the first occurrence of each prefix sum. This will help us efficiently track and retrieve the necessary information as we process the array. With the transformed array ready, the next step is to iterate through it while maintaining a running prefix _sum. At each step, we update the prefix _sum by adding the current value from the transformed array. To optimize the process, we store the first occurrence of each prefix _sum in the prefix _map, ensuring that each unique prefix sum is only recorded once. This allows us to quickly determine the earliest point in the array where a given prefix sum was encountered. Now, to identify well-performing intervals, we check the value of prefix _sum at each index. If prefix _sum is greater than 0, it means the subarray from the start up to the current index has a positive sum, making it a well-performing interval. In this case, we calculate its length as I+1 and update the maximum interval length if needed. If the prefix _sum is not positive, we look for an earlier prefix sum that is 1 less than the current prefix _sum. This is because subtracting 1 indicates the possible start of a new interval where the sum becomes positive. If such a prefix sum exists in prefix underscore map, we calculate the interval length using the indices and update the maximum length accordingly. This process ensures we efficiently identify the longest well-performing interval without repeatedly recalculating sums. Finally, after iterating through the array and checking conditions at each step, the algorithm concludes by returning the longest well-performing interval length stored in max_length. This result represents the maximum span of consecutive days where tiring days outnumber non-tiring ones. To summarize, the prefix sum technique is pivotal to this solution. By reducing the problem to prefix sum lookups, we avoid the inefficiency of recalculating subarray sums repeatedly. Additionally, the use of a hash map to store the first occurrence of each prefix sum ensures constant time complexity for these lookups, significantly speeding up the process. A few edge cases are worth noting. If all days are non-tiring, meaning all hours are 8 or less, the result will be 0 since no well-performing interval exists. On the other hand, if all days are tiring, the entire array qualifies as a well-performing interval. For a mix of tiring and non-tiring days, the algorithm efficiently determines the longest interval by leveraging the prefix sum and hash map combination. These insights, along with the careful use of data structures like arrays and hash maps, make the solution both elegant and efficient. When analyzing the complexity of this algorithm, we find that it performs exceptionally well. The time complexity is O(n), where n is the length of the hours array. This accounts for the single pass to transform the array, another pass to compute prefix sums, and the final pass to identify well-performing intervals. Each of these steps is linear, resulting in an overall linear time complexity. The space complexity is also O(n), as the hash map stores at most n entries, one for each unique prefix sum encountered during the iteration. These efficient time and space complexities make the algorithm suitable for large inputs. By transforming the array, leveraging prefix sums, and using a hash map for quick lookups, the solution achieves an optimal balance between clarity and performance. This solution efficiently computes the longest well-performing interval by leveraging a prefix sum approach and a hash map. Here's how it works. 1. Initialization asterisk. Prefix underscore sum keeps track of the cumulative score for the hours worked so far. A day with hours 8 contributes +1, while hours equals 8 contributes -1. Scene stores the first occurrence of each prefix underscore sum. This helps efficiently determine the length of a valid subarray. Max underscore length is initialized to 0 and will store the length of the longest well-performing interval. 2. Iterating through the hours array asterisk. For each day, update prefix underscore sum to reflect the current day's contribution. If prefix underscore sum becomes positive, it means that the interval from the start to the current day is well-performing. Update max underscore length to I+1, since the interval length is I-1. If prefix underscore sum is not positive, check if prefix underscore sum 1 exists in scene. If it does, it means there's a previous point where the score was smaller, and the interval between that point and the current day is well-performing. Update max underscore length accordingly. Store the first occurrence of prefix underscore sum in scene if it's not already present. This ensures we always use the earliest occurrence to maximize the interval length. 3. Return the result asterisk. After processing all days, max underscore length contains the length of the longest well-performing interval. This approach is efficient with a time complexity of O(n), where n is the length of the hours array, as we make a single pass through the array and perform constant time operations for each element. Here, we begin our Java implementation of the longest well-performing interval problem. The solution starts by initializing a prefix sum variable to 0, which will help us track the cumulative balance of tiring versus non-tiring days. We also define a hash map called scene to store the first occurrence of each prefix sum. This is crucial for efficiently calculating the length of well-performing intervals. Additionally, we initialize a variable max length to 0, which will store the maximum length of such an interval as we process the input. Next, we iterate through that hours array using a for loop. At each step, we update the prefix sum by adding 1 if the hours worked on a given day are greater than 8, or subtracting 1 otherwise. If the prefix sum becomes positive, it means the interval from the beginning up to the current index is well-performing, so we update max length to the maximum of its current value and the length of this interval, which is I+1. Otherwise, we check if there exists a smaller prefix sum that was previously seen and is one less than the current prefix sum. If such a value exists, it indicates that a well-performing subinterval ends at the current index, and we calculate its length by subtracting the index of this earlier prefix sum from the current index. We then update max length accordingly. Finally, if the current prefix sum has not been encountered before, we store its first occurrence in the scene map to ensure we always have the smallest index for future calculations. After completing the iteration through the input array, the function simply returns the value of max length. This value represents the length of the longest well-performing interval found in the given hours array. The use of a prefix sum combined with the hash map ensures that the solution is efficient and operates in O(n) time complexity, where n is the length of the input array. By leveraging the properties of prefix sums and the hash map, we are able to identify well-performing intervals without needing to check every possible subarray, making this approach highly optimal for large inputs. We start with the input array hours equals 9, 6, 9, 9, 6. First, we initialize our variables. The prefix _sum is set to 0, which will help us track the net balance of tiring versus non-tiring days. The scene dictionary is initialized as empty to store the first occurrence of each prefix _sum value, which will be crucial for determining intervals. Finally, max _length is set to 0 to keep track of the length of the longest well-performing interval. Now, we begin iterating through the array. At index 0, the hour is 9, which is greater than 8. This means it's a tiring day, so we increment prefix _sum to 1. Since prefix _sum 0, it indicates that the interval 0, 0 is well-performing, and we update max _length to 1. We then add this prefix _sum value of 1 to the scene dictionary with its index, resulting in scene equals 1 o'clock. Moving to index 1, the hour is 6, which is less than or equal to 8. This makes it a non-tiring day, so we decrement prefix _sum to 0. Since prefix _sum equals 0, we check if prefix _sum 1 equals -1 exists in scene, but it doesn't. We then add this prefix _sum value of 0 to scene, giving us scene equals 1 o'clock, 0, 1. At index 2, the hour is 9, a tiring day, so we increment prefix _sum to 1. Since prefix _sum 0, the interval 0, 2 is well-performing, and we update max _length to 3. At index 3, the hour is again 9, another tiring day, so we increment prefix _sum to 2. With prefix _sum 0, the interval 0, 3 is well-performing, so we update max _length to 4 and add prefix _sum equals 2 to scene, resulting in scene equals 1 o'clock, 0, 1, 2, 3. At index 4, the hour is 6, a non-tiring day, so we decrement prefix _sum back to 1. Since prefix _sum 0, the interval 0, 4 is well-performing, and we update max _length to 5. Finally, the output for this example is max _length equals 5. Now, we turn to a new example with the input hours equals 6, 6, 6, 9, 9. We initialize our variables again, prefix _sum equals 0, scene equals, and max _length equals 0. At index 0, the hour is 6, a non-tiring day, so we decrement prefix _sum to -1. Since prefix _sum equals 0, we check if prefix _sum 1 equals -2 exists in scene, but it doesn't. We add prefix _sum equals -1 to scene, resulting in scene equals -1, 0. At index 1, the hour is again 6, so we decrement prefix _sum to -2. Again, prefix _sum equals 0, so we check if prefix _sum 1 equals -3 exists in scene, but it doesn't. We then add prefix _sum equals -2 to scene, giving us scene equals -1, 0, -2, 1. At index 2, the hour is 6, another non-tiring day. We decrement prefix _sum to -3. Since prefix _sum equals 0, we check if prefix _sum 1 equals -4 exists in scene, but it doesn't. We add prefix _sum equals -3 to scene, resulting in scene equals -1, 0, -2, 1, -3, 2. At index 3, the hour is 9, a tiring day. This increments prefix _sum to -2. Since prefix _sum equals 0, we check if prefix _sum 1 equals -3 exists in scene. It does, at index 2. This means the interval 3, 3 is well performing, so we update max_length to 1. At index 4, the hour is 9, another tiring day, so we increment prefix_sum to -1. Again, prefix_sum equals 0, so we check if prefix_sum 1 equals -2 exists in scene. It does, at index 1. This makes the interval 2, 4 well performing, and we update max_length to 3. The output for this example is max_length equals 3. In this example, the input is hours equals 99666. As always, we initialize prefix_sum equals 0, scene equals, and max_length equals 0. At index 0, the hour is 9, a tiring day, so we increment prefix_sum to 1. Since prefix_sum 0, the interval 0, 0 is well performing, and we update max_length to 1. We add prefix_sum equals 1 to scene, resulting in scene equals 1 o'clock. At index 1, the hour is again 9, so we increment prefix_sum to 2. With prefix_sum 0, the interval 0, 1 is well performing, and we update max_length to 2. We also add prefix_sum equals 2 to scene, giving us scene equals 1 o'clock, 2, 1. At index 2, the hour is 6, a non-tiring day, so we decrement prefix_sum to 1. Since prefix_sum 0, the interval 0, 2 is well performing, and we update max_length to 3. At index 3, the hour is 6 again, so we decrement prefix_sum to 0. Since prefix_sum equals 0, we check if prefix_sum 1 equals -1 exists in scene, but it doesn't. We add prefix_sum equals 0 to scene, resulting in scene equals 1 o'clock, 2, 1, 0, 3. At index 4, the hour is 6, so we decrement prefix_sum to -1. Again, prefix_sum equals 0, so we check if prefix_sum 1 equals -2 exists in scene, but it doesn't. We add prefix_sum equals -1 to scene, giving us scene equals 1 o'clock, 2, 1, 0, 3, -1, 4. The output for this example is max_length equals 3. The time complexity of our optimized solution is O(n), where n is the length of the input array, hours. This efficiency comes from the way we process the data. First, we iterate through the array using a single for loop, which runs exactly n times, contributing O(n) to the total complexity. Within this loop, we update the prefix_sum for each element, and this update is done in constant time, or O(1). Next, we evaluate conditions like whether prefix_sum is greater than 0 or if a specific value exists in the dictionary. These are dictionary operations, and under the assumption of a good hash distribution, both membership checks and value retrievals take average case O(1) time. Finally, we store the prefix_sum in the dictionary with the operation scene, prefix_sum equals I. This is another dictionary operation, also averaging O(1). Since the operations inside the loop are all O(1), and the loop itself runs n times, the overall time complexity is O(n). The space complexity of our solution is O(n), where n is the length of the input array hours. This is primarily due to the use of the dictionary, scene, which stores the first occurrence of each unique prefix_sum. In the worst case, if all hours are either always greater than 8 or always less than or equal to 8, the prefix_sum could take on n distinct values, requiring the dictionary to store n entries. This results in O(n) space usage for the dictionary. As for the other variables, prefix_sum and max_length each take constant space, or O(1). Since O(n) from the dictionary dominates any constant space usage, the overall space complexity of the solution is O(n). To understand the efficiency of our optimized solution, let's compare it to a brute force approach. In a naive solution, we would check every possible subarray of hours to determine if it is well performing. This involves O(n) squared subarrays, and for each subarray, we would check its conditions, which could take O(n) time in the worst case. Multiplying these, the brute force approach has a time complexity of O(n) cubed. In contrast, the optimized solution leverages a prefix sum and a dictionary to track the first occurrence of each prefix sum. By doing so, it avoids the need to repeatedly check subarrays, reducing the number of operations significantly. The problem is solved in a single pass through the array, with constant time dictionary operations, resulting in a time complexity of O(n). Now let's analyze the best, average, and worst cases for our solution. In the best case, all hours are greater than 8, so the prefix sum is always positive. Here, the entire array forms the longest well-performing interval, and the dictionary is never used to check for smaller prefix sums. However, the loop still executes n times, so the time complexity remains O(n). In the average case, we have a mix of hours greater than 8 and less than or equal to 8. The algorithm performs some dictionary lookups for prefix sums, but these operations remain efficient, maintaining the average case complexity at O(n). In the worst case, the prefix sums are mostly unique, such as when hours alternate between values greater than 8 and less than or equal to 8. The dictionary grows to its maximum size, requiring O(n) space. Despite this, the time complexity stays O(n) due to the constant average time for dictionary operations. To summarize, the for loop runs exactly n times, and each dictionary operation, such as insertion or lookup, averages O(1). This makes the total number of operations proportional to n, solidifying the time complexity as O(n). The optimized approach is therefore highly efficient, with both time and space complexities of O(n), a significant improvement over the brute force method. In this problem, there are several common mistakes to watch out for. First, misunderstanding the problem constraints can lead to inefficient or failing solutions. For example, if you don't account for large input sizes, your code might time out, or it could crash on edge cases like empty arrays. Next, using unnecessary nested loops is a frequent pitfall. Brute force approaches with O(n²) or O(n³) complexity are often impractical for inputs where n exceeds 10,000. Instead, you should focus on optimized algorithms like sliding window or prefix sums. Another challenge is handling edge cases correctly. Scenarios such as arrays with all negative or all positive values, or even arrays of size 1, require careful testing to ensure your solution is robust. Improper initialization of variables is another source of errors. For instance, initializing tracking variables like max_sum or count incorrectly can lead to unexpected results. Lastly, assuming the input array is sorted without any guarantee from the problem statement can cause logical issues. Always verify the constraints and conditions provided before making such assumptions. Now, let's talk about key insights that can help you during coding interviews. First, focus on recognizing patterns. Many problems involving intervals or subarrays share common techniques such as sliding window, prefix sums, or hash maps. Identifying these patterns early can save you valuable time. Additionally, while brute force approaches are useful for grasping the problem initially, you should quickly identify their inefficiencies and transition to optimized solutions. Interviewers appreciate when you explain this thought process clearly. Don't forget to communicate edge cases explicitly. Mentioning scenarios like empty arrays or arrays with uniform values signals thoroughness and builds confidence in your approach. Finally, be prepared to discuss trade-offs. For example, while a hash map reduces runtime by enabling faster lookups, it comes at the cost of increased space complexity. Being able to articulate these trade-offs demonstrates a strong understanding of your solution. There are also several related problems that you might encounter, which use similar concepts. For instance, LeetCode 525, contiguous array, is another prefix sum problem but with slightly different conditions. LeetCode 560, subarray sum equals k, focuses on subarray sums and also applies prefix sums. LeetCode 209, minimum size subarray sum, uses a sliding window approach to minimize subarray length. Similarly, LeetCode 1248, count number of nice subarrays, combines sliding window and hashing to solve a subarray problem. In terms of alternative approaches, sliding window is a powerful technique for optimizing contiguous subarray problems. It allows you to dynamically adjust the range of indices, significantly reducing time complexity from O(n²) to O(n). However, it might require additional space for tracking variables. Another option is the prefix sum combined with a hash map. This approach converts the problem into cumulative sum computations, enabling faster interval lookups. While this method reduces runtime, the trade-off is higher space complexity due to the hash map. Finally, binary search on sorted prefix sums is another alternative approach for certain problems. This method is particularly effective when the problem involves sorted constraints. By pre-processing the prefix sums into a sorted structure, you can use binary search to efficiently find intervals. While this approach can be highly optimized for specific scenarios, it does come with trade-offs. Sorting the prefix sums or performing pre-processing adds computational overhead, which might not be ideal for all use cases. Always evaluate whether the additional complexity is justified based on the constraints and requirements of the problem. Great work! We've successfully solved the problem and learned how to use hash maps for efficient interval calculations. Remember, practicing these types of problems will strengthen your problem-solving skills. Don't forget to like and subscribe for more helpful content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!